right, picking back up with electric shock. So electric shock is the damaging effects resulting from current passing through a body. So very often people mistake the fact of high voltage as being what is going to be, life-threatening. It's not actually the voltage that is dangerous, it's the current that is the dangerous part of electricity. So in a previous lecture, I talked about the fact that you can have very high voltage on something like a balloon, but yet it's not dangerous because it doesn't have enough coulombs, enough electric charge on it. And that's exactly what we're talking about here. Current comes from the amount of charge flowing through, a wire. And so you need to have current, you need to have coulombs in order to have something like electric shock. So what causes it? What causes electric shock is what we call contact with ground. So the current has to pass through the body into an area that would be grounded. It needs to allow the current to flow. If there's no way for it to flow, that is what will keep it from making large damaging effects. This is why people who wear or work in a lot of electrical fields usually wear big thick boots and work with mats and things underneath of them. They will also attach what they call grounding wires and so forth to themselves. It's so that there's somewhere for that electricity to flow other than through their body. The thing is that the resistance of the human body varies. We can actually handle some current because we actually have pretty tough skin. Our resistance is 100 ohms if we're soaked in salt water. That's because salt water is very conductive. With the salt ions like sodium and chlorine, those ions, they're charged and they're really good at transferring electrical charge. However, if our skin is dry, our resistance goes up to 500,000 ohms. So that's a huge difference in resistance. Our skin is pretty resistant as far as, electric shock goes. Thing is that you can't feel 12 volts with dry skin. So if you have a 12-volt battery, for example, and you put your fingers on the two terminals, you're not going to feel it. It's not enough potential difference for it to punch through your skin. 24 volts, you'll feel a little tingle. And you might be thinking, yeah, but Professor B, I've licked a 9-volt battery and that hurt. Well, that's because you licked it. Your tongue is wet and so therefore has less resistance because you've got the water there along with some salts and things like that. And so that decreases your resistance on your tongue. In fact, you can feel a 1.5-volt battery if you have it in the right place in your mouth. One of those AA batteries. I don't recommend you do that, but you can feel it if you have it in the right contact places because your resistance is so low in your mouth. But yeah, you can feel a 9-volt battery. It will sting because your resistance is lower in your mouth. So what do we have for electric current effects on our body? Well, you can feel current that is really low. In fact, current is the problem. Voltage isn't the issue. It is the current. So you can see that it's very small, 0.001 amps we can feel, and 0.005 amps becomes painful. It becomes dangerous once you get up into the 0.01 to 0.05 because this is where you start to have issues with your muscles. And then if you get hit with 0.07 amps, if it goes through your heart, that can cause serious disruption and it can be fatal if it lasts more than a second going through there. So let's talk about that electric eel that we had earlier. because I told you that it produces 650 volts. It does produce 1 amp. So it produces more than what we can handle for 2 milliseconds. So it produces enough current to be dangerous for us. However, like I said, it's mainly discharged by the water around it, which is why it hasn't been found to be dangerous to us, because we usually are around them if they're in water. We're not like holding on to them outside of water, and they're not discharging out of water. I will post a video on electric shock, so if you want to know some more about how it works and how it can be really dangerous, you can find out some more. So if electric shock is so dangerous to us, if we, for example, touch a live wire from the house, this is why you turn off the power when you do work on electrical, because the current is enough to be incredibly dangerous to us, because there's enough voltage and enough current coming through your house circuits. Why can birds sit on power lines? Because if there's enough voltage and current coming through our house circuits, there's definitely more current and voltage coming through power lines. So why can these birds sit on the power lines and not get fried? Well, the thing is that electric shock requires a difference in electric potential. So it's not just the voltage that's the issue and not just the amperage that's the issue. You need to give it that ground. You need to give it somewhere to flow to. And when a bird is sitting on the wire, both of its feet are connected to the wire. And so there's no difference in potential between its feet. The same electric potential is there for both feet. Also, no part of the bird is touching anything else. So if that bird had incredibly long legs and could put one leg on the power line and one leg on the ground, then he'd be toast, because he would give that current, that electricity, a pathway to travel from the line through the bird to the ground. So that's why birds aren't going to get shocked. So how do we protect ourselves from electric shock? Well, there's lots of ways that we've done this. So every electric device is actually going to need 2 wires. So I don't know if you've ever wired anything, like putting together a lamp or something like that, but you need 2 wires in order to get the light bulb to work. And this is because from your outlet, there are 2 wires, right? There's 2 holes. One of those is carrying an energized wire from the electric company, right? So it's coming into your house and that wire goes to your outlet and it's carrying the energized, the electrical energy to that outlet. The other wire, these are the minimum wires you need, is a grounded or neutral wire that maintains the potential difference between the 2 wires. So you need those 2 wires in order to be able to make that potential difference. You've got the one coming in with the electricity, and then you have one going out that is going to be able to help create that potential difference. So if you think about it, in the plug, if you've ever opened one up, there's a wire that comes in for the plug, and then on the other side, the other half of the plug has a wire that's wired to it that goes out. And so you need those 2 wires to create those 2 parts of it. And when you put the plug in, it's going to help create the circuit, right? It'll connect those 2 wires to the wires in your device that are also doing the same thing. So that brings us to 3-pronged plugs. So every plug has those 2 wires in it, right? One that attaches to the energized wire from the electric company, and one that's the grounded wire in the wall, and then the plug plugs in and touches those. The 3-pronged plugs it's got the one for the energized wire, it has a neutral, and it has a ground. So these guys have an extra safety feature to them. So don't cut that off because it's there for a purpose. It's there for an extra ground so that there's an extra pathway for the extra electricity to go in case something happens. If you don't have a 3-prong plug in your wall, there are converters for that. You can buy a little converter plug to plug on to this plug that the ground will fit into, and it's got a little tab on it so that it'll sit against the wall in the plug on your wall. The other kind of plug is a polarized plug. You'll see these especially in modern houses. Older houses won't have the outlets for these, but our appliances have them. And this is so that the plug goes in the right way. So the small prong is wired to the load wire. So that's the energized wire, so that the switch will turn off the current. So the switch in the actual device will turn the current off through the circuit. And that's just so that it always is going to flow the same way, and that the switch is going to actually shut off the current to the device rather than allow the current to run through the device and then turn off. In case there's something that happens in the wiring, you don't have live current going into the device even though it's turned off. You've probably seen these around, and you may or may not understand why they're there, other than most people find them to be an annoyance because they will turn things off. These are called ground fault interrupters, or GFI outlets. These are actually there for your safety. You're usually going to find these near wet areas. So you're going to find them outside. You'll find them in kitchen areas or bathroom areas. I have them in my garage as well because it's a more damp area. What this does is it monitors those load carrying and ground wires for differences in their current. So it's got those two hooked into it, and it's measuring the difference in the current, because the current should be the same. When it's going, the current should be the same through those wires and not alter. If a difference is detected, that means something's gone wrong. There is too much current flowing, something's overheating, whatever it might be. It's going to trip and open the circuit incredibly fast. It's opening the circuit right here at the outlet. We'll see what happens if you've got other ways to open the circuit, but this is going to open the circuit incredibly fast right there to help protect you from an electric shock. So this is faster than the fuses and the circuit breakers that we're going to see. You've probably heard of circuit breakers. Those have to travel, the signal has to travel all the way to the circuit breaker, which may be in your basement or a completely different part of the house. This is going to trip right there and cut the current so that whatever is happening will stop right then and there. Some of these are set up to turn off the entire circuit that they're on. A lot of the modern ones are set up to only turn off that specific outlet because that's where the problem is. And when you hit the reset button, you're basically just closing the wires back up so that the circuit can work again.